Thank you for the introduction. Very, very kind. I'm glad to be here, introducing the North American part of this talk. I will talk about the CityLearn challenge. I will talk more about CityLearn, and then I'll throw in the challenge at the end. I would say it's good to be back in Switzerland, albeit virtually. So hopefully I can live up to the expectations. So, what are we talking about? My group at UT here does a lot on applied machine learning methods, basically within the scope of facilitating the energy transition. You can read all about these, on our website if you're interested. The talk today, as was introduced, will focus on reinforcement learning. This is not the slide here shows it's 1/4, but really it's more than 75% of the work that we do. And so really trying to understand how we can use reinforcement learning in this energy transition, using energy more sustainably and, when we need it. A few things that I like to throw out every now and then. When it comes to buildings, we just have to make ourselves clear that they use a lot of energy. This is from the US EEI, and it is for US particularly, but it's not far off from any other place. Especially when we're talking about the general sustainability and strategy, which is to move everything to electricity, heating, cooling, and then decarbonize the grid. So we will use more and more electricity. So it means we will need more and more generation, or think about how we can use the energy more sustainably. But what the point is that, the buildings and the building stock, as was shown in the talk before as well, has a huge impact. And so anything that we can do to address that, how we use energy more efficiently over time in the building stock will be beneficial to the good energy transition. There are a few things we can do. The first is efficiency. This is what we've been doing, forever. It is mainly talking about, doing more with less energy, building more efficient buildings, using more efficient appliances. And what we do is we reduce the overall demand in our buildings. So that's the green line, the green curve there. Then over time, we started saying, well, wouldn't it be nice if we start to, also generate our own electricity? So we start putting PV on our roofs, or basically everywhere. And we start getting this dip in the middle of the day, on sunny days, especially in places that have a lot of solar panels, places like California and Texas, slowly also starting, which we started to call the duck curve. And during the day, you have a lot of energy that you cannot use almost. You go into negative demand. And then you have to ramp up really quickly with the removal of the solar power and then the increasing demand, especially on the residential side. So there's a clear mismatch between the demand and the supply. And this is not news, I hope, to most of you all out there. Then the next level is the one I want to talk about, which is when we start thinking about, well, clearly the problem with renewables is that we don't have demand and generation at the same time. And so we need to shift. And the way we shift is through buffers, right? And so the question is, what it shows here is that the blue curve is where we want to be, roughly where we have a more constant generation or demand over the whole day or, over longer periods of time, which makes it a little bit more predictable, which makes it more predictable for the power plants. We don't need to build more peak power plants because we generate usually the power for peakers. And so it's a lot more predictable, really. But then the question becomes, well, how do we get here, right? And like I started saying, one thing we need to have is storage in order to be able to shift. This can be passive or active. And on the top of that, not only we need storage, we also need to make sure we understand how it works, we understand how we control it, and we don't mess up things by, moving everybody's load an hour later or earlier and then just creating a new peak. And so we need to, coordinate a little bit. And it's a really hard problem between buildings because as the previous speaker has introduced, there will be a lot of buildings, if you think this through, prosumers, right, that generate electricity, that use electricity, that may be storing electricity. And so creating some sort of coordinated effort will be really hard. And so that's the kind of problem that we're trying to addressing. And The method we're trying to use is deep reinforcement learning, or RL, model-free, for the reasons that model-based will require us to generate a lot of data from a lot of people, and it will be a little less easy to integrate over larger scales, I think. This is debatable. There are a few people after me who also would speak about RL, and I think that's a really interesting topic. So hopefully you'll stick around for those, really the experts in their field. So it's really excited to be part of that lineup. So without going too much into detail, right? RL, you get a set of states and you do actions, and then you get a reward for that. And the way you shape your reward function will determine what actions you take in the future. And so by that, you can kind of learn what to do. And there's a lot going on, and I don't want to talk into details, but I want to show you what's possible, right? So we started looking into this. Actually, one of my last works at ETH was looking into a low-X building by Professor Leibengut. We did some control on that, but that's another story. So I will not talk about that. We started looking into deep RL on this larger scale and looking, what can you do in this demand response sort of like applications when you have many buildings and you try to control the demand. And so we started first looking into papers what are people who do it, right? As you do. And so what we found is there's a lot going on, but there is almost nothing comparable. So and we did our own, right? So we went to the same exercise, we did our own thing, and let's face it, nobody really cares because nobody can compare it. And so what we ended up doing then is take a break, take a step back, and build an environment instead of a solution, and then use that environment to be able to study the problem in a way that we can compare it. And so we ended up building, what we call CityLearn. And that's a gym environment, and that's a standard environment to use RL problems, or to be working in RL problems and create benchmarks and standardizations. And so we said, well, we want the buildings to stay the same. We created this overall structure of heat pumps, electric heaters, chilled water storage, domestic hot water storage, solar arrays. So just about a month ago, we also released electric storage and EVs, so we can create a full electric fleet. The number of the buildings doesn't matter. It just, it's just on your end on the computational side. And you can change what type of systems you have. So the system side, you're free to do. And then the energy side of the building side is given, so you don't need to worry about it. And that's kind of like, what is mentioned here is you abstract out the buildings, you don't need to worry about it, and you can study all kinds of different problems, right? The centralized problems where you have one controller that knows everything, kind of like an aggregator, or completely decentralized agents just to see what's going on if you don't do anything. But at the end of the day, what we do is energy storage control, like when do you charge and when you discharge your chilled water and your domestic hot water and your batteries or your EVs. And so, and you try to do that in a way that it is on the aggregated scale, it's beneficial to the grid. The overall objective, right, is scalable, plug and play, kind of like controller, which mentioned it, so you can get started without having to have a lot of data, and then over time you can get where you want to be. This may not be this might be a controversial take, but that's one that we're trying to explore. So a lot going on. Again, this is kind of like the setup. We put the technical paper that summarizes it on archive. So you can look at it. That just goes what's under the hood, basically. And then there's also a few papers that built this last year and the year before that summarize the work. But essentially, this problem of being able to coordinate buildings, integrating with the grid, all kinds of energy systems, and then also not every building having to be the same, being pretty unique, is kind of like the whole point of this. This year, we also added things like CO2 conversion, so we can not just work with energy, but also emission factors. And then also, electric storage, so we can look at this full electrification over time of buildings. That's pretty cool. It's all on that website, citylearn.net. You can check it out. And it's all free. Our IP people got all kinds of gray hair when I told them everything's free. So, but this is for the good cause, so I don't care about patents and all that shit. So we want to make sure that this is diffuse and people are using it and then comparing their own results. So what can we do with it? Here's an experiment or an example. 9 buildings, microgrid. There is 5 at the bottom. Those are multifamily homes. And then the other 4 are commercial buildings. And you see the PVs are a little bit scattered, 2 on the residential ones and 2 on the commercial buildings. And so, the goal is now to see what we can do. And again, without going too much into detail, this is for cooling climate. Sorry, I think it's New Orleans. On the left-hand side, you have this typical spring load with the average, and then the deviation. So that's all the buildings. In the middle, you have the summer with the higher peak, and then the winter load on the right-hand side. This is if you have no control, so just the demand of the buildings. Clearly, in a cooling climate, the summer peak is the more important one. Now, if you do what usually is done, and you take your heat pumps and you do like a really good optimization, or you do something where you say, well, it's cheaper to do it at night, so we charge the storage at night, and then we release it during the day, which is kind of like standard. So this shows you what you'd expect, right? The peaks will all move. You will get almost the same peak, just at a different time, which maybe not what you're looking for, but essentially, by moving everything into the night, these are optimized to be done storing at like 7 a.m. in the morning, which is usually when you're switching at tariffs also in the morning and the day. So basically, no reduction really on the peak, but a little bit on the conversion. Then if you do it in a smarter way, you see the orange curve in the middle. So again, these are the agents that are working a little bit together, a little bit independently. And so you can see that the curve, that orange curve, starts to resemble a lot like that blue one that I copied back at the bottom there that I mentioned you in the beginning. So what are you looking at, spring, summer, or winter? The curve starts to flatten quite a bit, and the peak drop is dramatic. And if you look at the summer peak drops, almost 30-40%, which is quite substantial, because it means you may not have to buy another power plant for that peak that's increasing. So this is pretty cool, and it's kind of like makes us think about doing more, and we're very excited. So there is a lot going on under the hood. We can talk a lot about how do you want to share information between the buildings or not. So in this paper at Buildsys, we did a little bit of sharing, just so we have some knowledge of what's going on, but it's done in a way that you don't need to give up privacy. So that's kind of like an important part. And you're welcome to read that. You're welcome to go on YouTube and watch a video of the paper, or the PhD defense about it. That was also ready to go. So a lot going on. The last thing I would say, again, the CityLearn challenge itself is online now, so you can sign up and you can compete against others to find the best controller. This year we have up to $3,000 in prize money. So, maybe you can win something and then use it to travel once we're allowed to travel again. But, I'm excited because people are using it. We used it in the summer school. The last time before we were able to travel, people are starting to, write papers with this. People are putting things on top. I recently saw somebody putting a grid on top of our environment, which is kind of cool. And I see my time's up, and I will say the last thing is we also organized a workshop around this topic of reinforcement learning in buildings. Last time at Buildsys, about 100 people were there, which is pretty cool. If you're interested, next edition will be in Portugal. Fingers crossed in November, hopefully. And we hopefully to see you there soon. CFP will come out soon. If you need more, look at our website. And with that, I'm ready to take some questions.
Great. Thank you, Zoltan, for the presentation. Quick question, as questions will come up in the Q&A. Is there, for those of us which are not so familiar with reinforcement learning, is there a very sort of basic and clear description between model-based and free RL?
Right.
I mean, are both of them relying in a sort of state transition matrix like classical Markov decision processes, or what is the core difference?
The core difference is that when you talk about model-based, you're creating the model, and then you're using that model to make a forecast into the future and then make a better decision. It's very similar to MPC, where you create the model, you forecast what will happen over your control horizon, and then you take the first step down the road. So that's the main difference. And by needing to build a model, you need to generate a lot of data, and you end up with the same problem that MPCs have, is that you need the data and you need a good model for your decision. So it's a bit of I think it's an open question right now, where we're going. I think, like I mentioned before, Jan is coming up pretty soon. I think he's got the right idea, is to sort of create a mixture between models, or use simplified models because they help learn quickly, but then try to exploit the RL's ability to explore the space efficiently, to increase learning, because complete model free will just result in chaos, right? So you need kind of like a driving force.
Great, thanks. And a little bit in the lines of a question in the Q&A, which asks about whether the code is open source. Yeah, again, for those of us that are not so familiar with OpenAI Gym, I think it's the case. Is it like people build their models and then they are run in your central computation, or is it like people submit a set of results with some information you give them, like in Kaggle, right? That you sort of have like a competition, and then I believe you make the calculations yourself and then submit results. Do they have to develop their models in your platform, or if you could give some insight on how it works?
Yes, and so on. Right. No, absolutely. So the code itself, if we don't talk about a challenge, the code itself is a license, an MIT license. So do whatever you want with it. What I mentioned before, you can look at it, you can download it.
Like a beer license.
It's a beer license. I mean, if you make money off of it, it's good to some extent, because hopefully it helps, right? But yeah, the code is completely free. In order to use it, the gym environment is standardized for reinforcement learning control problems. So it has a standard interface, API, so you can say, get states and do actions and get rewards. And so that makes it easy to start. We also said, there's like stable baselines, what they call, so you can just run them without doing anything, and you can get started and then start modifying that. And you can also, because everybody who is doing research in RL creates their model or their controller agents in AI Gym, and so you can just plug them into another problem, basically. That's the whole point of this. So you don't have to recreate the environment, and you don't have to recreate the agents from scratch, but you can plug them from one problem into the other problem. And then the challenge itself, so we do it like Kaggle, but we haven't figured out a way to automatically score. And so what you have to do is create your agent file and then send it to us, and then we run it on our computers. That's the only thing that is very similar, but that's only for the challenge. If you just want to work yourself, just run it on your computer, or like Colab or Asia or something.
Super. So yeah, we have a question from Esther in the Q&A. And together with that, maybe I'll try to bundle a couple of more questions. So it is in the lines of how are the submissions evaluated, right? So how is this error band or sort of whatever metric is used calculated? And then, maybe we go ahead with this one about the error band, or generally speaking, the scoring of the submissions.
Yeah, so I mean, if you go to the website, I didn't talk about the individual scores, but we do a little bit. There's multiple things. So one thing we do is we have a 4-year case study. So it's not just 1 year that you simulate over and over again, but it's literally 4 years with individual weather data. So it's like a real example, not simulating the same year over and over again. And so we established the scoring in a way that, well, what is your best score at the end? So that's like the best controller, but what is the most stable one that is not, oscillating in the beginning? So what gets fastest to the environment? And then there's like some grid constraints like ramping scores and things like that. So I didn't show any of that because it's on the website and it's very technical a little bit. So it's it would take the time away. The bands that I showed in the presentation, those were just the min-max and the average of the summer data that we had for the simulation. That was not the agent's behaviors.
Okay. Okay. Good. Yeah. No, I think it was really a nice presentation, Zoltan. Thank you very much. If you don't mind, maybe we address one or two more questions. Of course, I think because many of us are curious about the benchmark, some of these questions and about the tool itself, some of the questions are a bit technical, and it's nice, although most of the information may be available, it's nice to hear a bit from you. So, for example, about the execution of the controller. If I understood you correctly, because there's a question about it, about where it is running. But I think you already said that basically sort of people run something and then they submit a sort of a configuration file that then you run and make.
Right.
And okay, super. So
you train and test on your own computer, and then you have one file that's called agent.py, and then you send us that, and then we just rerun that same code. Last year when we did it, we asked you to send us pre-compiled agents, and we just run the final agents. But this year we want to make sure, we want to work with the learning process. So what we actually do, I should say that, what we actually do is we change the buildings a little bit. So we don't evaluate your control on the exact same buildings, but we change the setup, we change the storage a little bit. So it's a slightly different problem, right? So you have to think about that. And you can do that yourself. You have access. You can change everything on the buildings. You can evaluate the robustness of your controllers. All the things we do are really annoying to everyone, but I think they are interesting because that's a real problem, right? When you start this, every building will be different, every user will be different. And so this kind of like robustness checks are where it's fun. Like how long does it take to be stable? Like how do you get there? How good do you get in the end? And then what happens if you take this and put it on another building that's almost the same, but not quite? And, does it still work or not? I think that's
definitely cool. Hey, if you allow me 1, 2 questions just before we go over to the transition and the last speaker. Again, technical stuff, and in the lines of with the spirit of motivating people also to participate in your benchmark. Have you experienced a very wide range of users, like from sort of the beginners to the very expert ones? And if one from academia wants to develop a new control algorithm, and in academia there is a little bit this of publishing and so on, do they have to somehow be sure that they publish before submitting? Is there any concerns in those lines? I'd like to hear your thoughts.
No, I mean,
go to a break.
Yeah. Right. No, I understand. Obviously, you can do whatever you want. Last year, we tried to encourage people to publish, that actually we want them to publish so people use it. This year, because we give out money, we will ask to upload their code. So then to make sure that it's shared. But, if there is a need to publish first, we can obviously work around that. But we have a constraint because we give out money. So now I'm bound to my sponsors a little bit. That like, oh, well, you can't just give money for nothing. You should show something. So that's that. But we're encouraging publication. So hopefully that's and sharing knowledge and resources.